Hello everyone, this is BV Hermit. Today we are going to discuss the last part of the ray optics, that is optical instruments. See, optical instruments are the devices like this which help us in observation and detailed examination of objects. To observe and to detailed examination, we need to use some devices or instruments which are called as optical instruments. These devices and instruments are designed using the process or using the phenomenon of refraction properties of the mirror or lenses like that. Then some of the optical instruments are given here. It may be a simple microscope or a magnifying lens, compound microscope like that, a simple lens, eye lens. This is eye lens, and spectacles. So torch lenses, telescopes. So these are the some of the example of optical instruments. Here, in which first one is a simple microscope. See, simple microscope is used for observing magnified images of the tiny objects. See, tiny objects is nothing but a small objects. So to observe or to study the magnified images of the small bodies, we are using this type of instrument, which is we can call it as simple microscope as shown in the figure. See, so this is one of the object which is a tiny, a small one. If you want to observe this object clearly, you need to expand this body, you need to expand the image, or you need to enlarge the image or a magnified image. To get the magnified image of this tiny object, we are using a simple microscope. According to definition, a simple microscope is used for observing a magnified image of these tiny objects, which is called as simple microscope. Here, a simple microscope consists of a converging lens. See, this is a converging lens. Also, we can call it as convex lens of a small focal length. Its focal length is taken as f. When object is placed very closer to the lens at a distance u from the optical center, then it is less than the focal length. See, this point we can call it as, these 2 points are we can call it as principal focus. The distance from the principal focus to optical center is called as a focal length. Then the object is placed very closer to the lens, that is less than focal length. Then in such a condition, the image is virtual, erect, and magnified image of the object is formed. See, this is the condition to get the enlarged image. That is, the object should be within the focal length, which is near to the lens. In such a condition, object is erect, virtual, and enlarged image or magnified image is formed. That is why a simple microscope is also called as magnifying lens. This simple microscope also we can call it as magnifying lens, which is used to see the magnified image of the small objects. That is the simple microscope. Here one definition is there, that is the angular magnification or magnifying power. So the magnifying power of a simple microscope is defined as, that is the ratio of angle subtended at the eye by the image to the angle subtended by the object. See, angle subtended by the eye divided by angle subtended by the object when both are at the least distance of the distinct vision or nearest point. That is, we can call it as magnifying power of a simple microscope or angular magnification of simple microscope. This is the one definition. See, actually what happens here in the simple microscope process? The path of the rays in a simple microscope as shown in the figure like this A. So in the figure A, the path of the actual image or a process is given here. See, there are two green points are here. One is here, another one is here, which are called as F and F, principal focuses. Then, which are present on these principal focus or foci, which are present on the principal axis. Then C be the here, actually this is the point we can call it as optical center, which is represented as a C, and object is present at a distance u. Then the distance from object to optical center, which is called as object distance. Then AB be the object, as we know that, which is placed between C and F here. Then which is a distance is taken as a u, such that the virtual erect and magnified image A dash B dash. See, this image is considered as a dash B. If object is considered as a AB, then its image is considered as a dash B dash. This image is virtual, erect and enlarged or magnified image is formed. The eye is held very closer to the lens, which is a normal adjustment to the image is formed at least a distance, at the least distance of the distinct vision or nearest point D. So for D, for the normal eye, see, so for the nearest point here at which, so you will get the image to the eye. So this is the working of the microscope. The magnifying power of a simple microscope M is equal to beta by alpha. Actually that is equals to M equals to 1 plus capital D divided by small f, where D is a distance from image to the optical center and F be the focal length of the lens. The next concept is a compound microscope. See, this is the compound microscope. So as shown in the figure, first we need to know that what is meant by compound microscope. Actually, compound microscope is an optical instrument. It is used for observing highly magnified images of a tiny objects. That is called as a compound microscope. See, there are some smallest objects are there. So we need to study the objects very clearly. In such a condition, we need a highly magnified image of that body. That's why we are using this type of microscopes to get a highly magnified image of such bodies. That is called as compound microscope. One second. See, once again I am explaining. A compound microscope is an instrument used for observing highly magnified images of the small objects, which is a compound microscope. The compound microscope consists of two converging lenses. Here, as shown in the figure, there are two converging lenses. One is objective lens, another one is eyepiece. The converging lens, which is also called as a system of lenses, in which first one is objective lens, which is represented by O, of very small focal length FO, and a small aperture. Then second lens is on, which is called as eyepiece, which is represented by capital A, of moderate focal length. Its focal length is moderate and a large aperture. The two lenses are held coaxially, which are present in a single axis, that is called as coaxially, at the free end of the tube at a suitable fixed distance. So these are the present at suitable fixed distance from each other. Then a distance of the objective lens from the object. See, this is an object, AB be the object, and distance from the objective lens to the object, which is called as object distance. And see, the tiny object AB, which is considered as a tiny object because its size is very small. A tiny objects AB be viewed which is placed nearest to the objective lens, or this is a slightly beyond the principal focus. See, this is a present slightly beyond the principal focus, and that is we can take it as a FO. See here, beyond this there is an object at this particular point. Here that is the principal focus, F naught. Then so the object is present beyond the principal focus, F naught or FO. The objective forms an enlarged this objective, so which forms an enlarged, see this is an object, its image is formed here. This image is A dash B dash, which is enlarged, nothing but it is a, its size is increased, and real image, but it is inverted, is formed. See, so this A dash B dash is act as an object for the eyepiece. See, this A dash B dash is considered as an object for this eyepiece. The position of the eyepiece is so adjusted that, which is adjusted like that, A dash B dash lies within the principal focus. See, this A dash B dash, which should be lies within the principal focus. This is a principal focus point which present within the object is present within this principal focus. That is a principal focus, the distance from the principal focus to eyepiece, which is called as, so focal length of the eyepiece, which is represented by FE. Now the eyepiece is act as a simple magnifying lens. Now this eyepiece, which is acting as a simple magnifying lens, and it forms the erect image, then virtual and enlarged image. This lens which forms the erect, virtual and enlarged image, which forms at A dash B dash. See, A dash B dash be the enlarged, virtual and erect image of this A dash B dash. This final image A dash B dash is seen by the eye held closer to the eyepiece. See, so this A dash B dash is observed to the eye, which is closer to the eyepiece. The adjustments are made such that the final image A dash B dash, see this is A dash B dash, which is formed at a least distance of the distinct vision, which is formed at least distance of distinct vision, that is taken as a capital D, or nearest point to the eye. So this is D, we can this D we can call it as a nearest point to the eye, and this is normal adjustment of the compound microscope. This is what we can call as a normal adjustment of the compound microscope. Here also again there is a magnifying power of compound microscope definition is there. According to this, that is the ratio of angle subtended by the eye by the final image to the angle subtended at the eye by the object, and both are placed at a least distance of distinct vision. So that is the definition of magnifying power of compound microscope. The magnifying power of the compound microscope, that is equal to M equals to the next one is a telescope. A telescope is an optical instrument which is used to see the distant objects clearly and magnified. That type of instrument we can call it as telescope. If the object is present so far from us, that is called as a distant object. If you want to see the object clearly and magnified, in such a condition we need to use the instrument that is called as telescope. In which astronomical telescope, nothing but these are the telescope used to observe heavenly objects like a moon, distant stars and planets like this. So if you want to study or observe these type of heavenly bodies, so we are taking the one type of telescope. That telescope we can call it as astronomical telescope. An astronomical telescope consists of two lenses. See here, there are two lenses are here represented like this. There are two lenses or a lens system. This is totally we can call it as a lens system or system of two lenses. In which first one is objective lens. This is an objective lens which is a larger in focal length, having a larger focal length and a large aperture. The second one is an eyepiece. This is an eyepiece which is represented by a capital A, having a small focal length and a small aperture. This is called as eyepiece. Then these lenses are mounted coaxially. See, so these mounted on one axis. Both are mounted on a single axis, that is called as a coaxially at a free ends of the two tubes. The distance between the lenses can be adjusted using a rack and pinion arrangement. So using these lenses are arranged. Then in a normal adjustment of the telescope, the final image is formed at infinity. See here. So during the normal adjustment, so you will get the image at infinite distance. That's why these rays are parallel. If the rays are parallel, definitely that is at infinite distance. See, a parallel beam of light from an astronomical object, it may be a star, moon, like that, whatever are some other planets. See, when a parallel beam of light, these are the parallel beam of light. When a parallel beam of light from an astronomical body at infinite distance is made to fall on the objective lens here of the telescope, it forms the real and inverted image, which is diminished one also. See here, so when the beam of light which is coming from the object, once which is a fall on the objective lens, which forms the image. This is the image. This image is formed, which is a real, inverted and diminished. Diminished is nothing but a small or the small. So this type of image is formed. This image is, we can take it as somewhat a dash b dash of the object. Object is considered as a AB, so its image is, you can take it as a dash b dash. Then eyepiece is also adjusted that a dash b dash is lies at the principal focus of the eyepiece. See, so this according to this image, so this eyepiece can be adjusted. This eyepiece can be adjusted such that so this object is lies on the principal focus of the eyepiece. Therefore, highly magnified final image is formed. So from this, the highly magnified so image is formed at the infinite distance. At infinite distance. See, the final image is the infinite at the infinite distance. The final image is obtained. That final image is erect with respect to a dash b dash. That is this one. So, but it is inverted. So that's why this is inverted image is formed at the infinite distance with respect to object. This does not matter because of the astronomical objects are normally spherical. The object, it may be the vertical or erect, it does not matter because so we know that almost heavenly bodies which are in the form of sphere or spherical bodies. That's why, so using this type of instrument we can use to observe, we are used to study the objects. So this type of instrument we can call it as astronomical telescope. Then next one is reflecting type of telescope. What is that reflecting type of telescope? Why it is called as a reflecting type of telescope? See, the modern telescopes use as a concave mirror. The last one is reflecting type of telescope, which is also called as Cassegrain telescope. See, in the modern telescopes, use a concave mirror as an objective instead of the lenses. So in the last case, like in astronomical telescope, we are using objective as a lens. But so the modern telescopes, instead of the lenses here, there is a use of the mirror. The concave mirrors are used in the place of objective lenses. Then here the mirrors are using in the place of objective lens, and these mirrors which reflects the rays. That's why these type of telescopes we can call it as reflecting telescopes or reflecting types of telescopes. In these reflecting telescopes, there is no chromatic aberration. What is that chromatic aberration? Chromatic aberration is nothing but, so if the lens, whenever a parallel beam of light which is entering into the lens, all the rays are merged at a point. But because of the refraction, all the colored light which is not able to focus on a particular point, there is a slight aberration takes place. So that's why, so there is some error is formed in during the case of lens. That's why, so here in the case of in place of lens, if we use the mirror, there is no chromatic aberration takes place. That's why, so in the modern telescopes, in place of lens, they are using mirrors. If the parabolic mirrors are used, there is no spherical aberration also. The image formed is much brighter. So see here, one more advantage to use the mirror. That is, if the image formed, if we use the mirror, then the image formed is much brighter and the resolving power is also much higher as compared to refracting type of telescope. That is lens used telescope we can call it as a refracting type of telescope. If we use the mirror, that is a reflecting type of telescope. Then such telescope is known as a Cassegrain telescope. It is named after its invention. Then see here, a reflecting type of telescope was initially designed by Newton. Then this model has been modified time to time. See, in Cassegrain telescope, there is a parabolic concave reflector of a nearly 5-meter diameter with a narrow hole at the center. Then parallel, so that is the actual mirror used in the telescope. When the parallel rays from a distant star or any planets which is entering the telescope, see here, so these are the parallel rays, so which are entering into the telescope from the distant bodies or distant heavenly bodies. See here, a parallel rays from a distant stars or planet, so entering the telescope in the direction parallel to the principal axis. See here, this is the principal axis here, so which is parallel to the principal axis, these rays are entering. Then so the mirror tend is actually, there is mirror is used which is tend to converge to its focus. See, this is trying to converge these rays, this is trying to converge these rays. So but so this is trying to converge these rays at a particular focus. but the before converging, see here, so when it entering into the telescope, after because of this mirror, that is a reflection takes place, and which is try to converge these rays at this point. But before going to converge at this point, they are reflected by a secondary convex mirror. See here, one more convex mirror is present here, this secondary convex mirror. So with this is, you can take it as a eyepiece. Then once the ray of light is entering and fall on the objective mirror, that is reflected, and which is fall on the secondary mirror, that is an secondary mirror. So due to this secondary mirror, these rays is reflected again, which is travel towards the eyepiece. This is a eyepiece. Then final image is seen through the eyepiece. Then the final image seen by the eyepiece is inverted with respect to the object. But it does not matter, because already told that astronomical objects are spherical. Thank you.